Okay. So hi everybody, my name is Noah Evans and I'm a member of technical staff at Sandia National Laboratories. So this talk is going to be a little bit different in that it's not a research talk so much as a practice and experience talk.
No, I think moving the microphone higher will help.
Why is that? Okay. That better? Okay. So how many people here know Sandia? So a decent number of people. So historically, Sandia comes out of Los Alamos. And the reason that it actually came from Los Alamos is because Los Alamos realized that while it could do the heavy lifting for the Manhattan Project, that it did not have enough labor to actually do all of the necessary engineering work to sort of to work on the stockpile. And so with that, it got spun off, and that is why, if you've ever seen Sandias, they're mitochondria. They live inside of larger bases where they provide engineering support, and now other support too, which I'll talk about later. And so another thing that a lot of people don't necessarily know about Sandia is that Sandia is what's called an FFRDC, so it's a federally funded research and development center, which means that as well as research, there's also a certain amount of refereeing that Sandia does. So we work with the government to develop legislation. We're not allowed to provide an advisory role, but we are expected to make legislation the best that we can using our technical expertise. But one interesting thing is that we're not actually government employees. The government owns everything, like our chairs, our computers, everything, but not us. We are actually funded by a consortium of Honeywell and the University of California, Berkeley, I believe. But the main job of Sandia, although it has multiple missions, it does a lot of cybersecurity work, it does a lot of space work. But sort of Sandia's bread and butter is that we are responsible for the safety, security, and efficacy of the nation's stockpile. And so that means that we care a lot that things are engineered correctly and that things will always work the way they're supposed to. And so this, you can sort of guess why we're getting to formal methods here. And so specifically the systems that we really care about are microprocessor-based systems, but they're roughly on the order of a dishwasher. So they need to wash a dish on time, they need to do some other things, but they're relatively simple. But these are not your house's dishwasher. These are dishwashers of Armageddon. So if you don't wash a dish at the right time, the world ends. So we really care that things always do what they're supposed to and never do what they're not supposed to. So it should have been obvious at the time, but it took Sandia a long time to really realize that formal methods matter. And so in the last 13 years, there's been a lot of developments with formal methods at Sandia. So about 13 years ago, Jackson Mayo and Ram Armstrong got together and like, oh, we should probably be doing this. And they started with a little bit of seed funding, and then that project was successful enough to management that we were allowed to continue. And then we did some forensic work where we checked out existing systems and we were able to show things that traditional testing weren't able to show. And that's as detailed as I can get here. But based on those successes, now we are fully integrated into Sandia's engineering and development workflow. So we are actually using a lot of the stuff that's being discussed here in practice. And we are pretty well funded now. We have about 25 to 27 members of staff working on formal methods right now. So we are the largest group in DOE and probably one of the largest industrial groups in the US. But I've given some background on Sandia, so now I'll talk a little bit about our system. So Sandia Technology is pretty much the best that the 1980s had to offer. So we are dealing with very heavily resource-constrained systems They're roughly on the order of like a 1980s workstation. So 5 to 10 megahertz, megabytes of RAM. Our firmwares are limited to about 100K. So this is like stuff that you'd be playing on with your Commodore. But this is actually really nice for formal methods because these are things that are tractable to the techniques we have today. But it's still not trivial to verify these things. Our firmwares are real-time. They have the very hard constraints that I talked about earlier and the very stiff requirements. And what's interesting is that a lot of the behaviors of our firmware are very similar to like an old NES. If you've ever tried to, who here has ever tried to program for an NES? Well, don't worry. But the most important thing about programming for an old video game system is that you really care when the TV is going to display a new scan line. And so we have to do all of our work before the scan line, and this is not soft real time, this is hard real time. It just gets washed or it doesn't, the world ends or it doesn't. And so, but the problem is that because we're so constrained, our code is very much spaghetti code, but we have been able to show that we can use POC-based and SMT-based workflows to get very strong, correct by construction, rigorous proofs of correctness for the firmware. But that leaves hardware. And so a lot of my work at Sandia has been building out and developing our hardware workflow. And so right now what we do is we mostly use SMT. Yosis in particular is indispensable. We can't use Get Jasper Gold or OneSpin because we need full observability into the systems that we use. So Yosis for this is a godsend because we know what every line of code does in Yosis. We can look at it. We have a license for Verific, so we can look at their code too. And we also can look at the SMT models and have some degree of assurance that the SMT models map to the original netlist and circuit that we gave it. And so in particular, we've had two very large successes with Yosis so far. One is with the RISC-V formal framework that came out of Yosis. So does everyone know it? Should I talk about it a little bit? The essence of it is that it provides a Verilog-based specification for RISC-V. So you can think of it as like a one-cycle processor that just describes the behaviors. And then it uses observation variables and SMT-based equivalents to show that this little one-cycle processor is exactly like your much more complicated processor. And again, I can't talk about this, but we found two very critical bugs in our systems using this. And so the efficacy of the approach is no longer in question. And we also have an ASIC specification that we're currently integrating. And so for the final thought, because I'm running out of time, what we'd really like in the future is a fully correct by construction MBD workflow for correct by construction systems. And what this really is something very similar to the workflows that Adam is proposing, where we have a more tractable formal language like Koika, where we can then specify using traditional Sandia systems engineering workflows, but where we refine those workflows to have actual formal intent rather than being sort of ad hoc, and then implement a actual refinement using COC down to something like Koika that has been amended so that it can use things like, it can describe things like bus-based systems, which was a lot of Tomas's Fifi work. So to wrap up, Sandia uses formal methods up and down the stack. In particular, we've had a lot of success with software. We're now trying to have similar success with hardware. We've used SMT and it's been very successful, but would really like to move to a deep spec on QED style. And I think that's exactly 10 minutes.
Yep.
So.
Thanks a lot. Okay, great.